Sorry. Okay, so good morning to all of you. Let us start our discussion for today's class. We are discussing the stability of the molecule, so structure and reactivity, and we started with the discussion of aromaticity and the related different terminologies and their definitions and examples and different related questions. Okay, today what we'll do is we'll try to look into more details of the one of the important part, that is homoaromatic and anti-homoaromatic compounds. Okay, so that discussion will be helping us to cover up the almost all the parts of the related topics. Okay, now just before going forward, those who are not able to hear my voice, just try to uh, check your microphone. Can anybody, one of you, just confirm me that am I audible?
Yes, sir.
Okay, okay. Then the student who is not able to hear me, it is the problem is with your own system. Just check it. Okay, and at the end, I'll be providing the recording of you of my class. Okay, so let us move forward. Now, in previous classes, what we have come to know, the homoaromatic, it has some specific features. Uh, Quickly, can anybody just tell what is the definition? If I try to summarize, the main differences of homoaromatic compound with the aromatic compound is, okay, so the main difference will be the conjugation will be observed by overlooking sp3 center or centers. Okay, this is the important part. Remaining other part will be similar. Since it is related to aromatic, it has to have 4n plus 2 pi electrons. It has to be cyclic in structure. Okay, and overall what has been found is that this homoaromatic compound is quite stable, but its stability is not more than the aromatic compound. Definitely, it will be less than aromatic compound. Okay, your extension of conjugation or pi delocalization is happening by overlooking sp3 center. Okay, which was not as convenient as what you have seen for aromatic compound. So that's why the stability will be less than aromatic, but its stability is more than non-aromatic compound. Okay, quickly, we have to first know, and we already came to know that definitely it is the aromatic compound which is the foundation of the homoaromatic compound, right? So we came to know that these are the different structures. Okay, this one, this is the 2, 3, 4, 5, and 6. Okay, these are the smaller cycle compounds or the reactive species, which is termed as aromatic, right? Cyclopropenyl carbocation, you have butene, cyclobutenyl dication, you have cyclobutenyl uh, dianion, you have cyclopropene dienyl carbanion. Okay, you have benzene, and you have uh, propylium carbocation. Okay, or cycloheptatrienyl carbocation. So these are the compound belongs to the aromatic category. So homoaromatic compound will be based on these. Got it? So they will be based on these structures. Only what you have to do, you have to have one or more than one sp3 centers connected, okay, but the base will be this one. Got it? Then the molecule will found to be the homoaromatic. Similarly, let us look at quickly the anti-homoaromatic. Now here, if you look at, this is the actually anti-aromatic is the base. Okay, so definition wise it is the similar, only you have the conjugation observed by overlooking sp3 centers. Okay, so delocalization, if you talk about, it has to be continuing by overlooking sp3 center or centers, so more than one center may be there. Okay, and stability wise it is definitely more stable than anti-aromatic, because anti-aromatic is the least stable compound, but it is less stable than non-aromatic. So non-aromatic is more stable than anti-homoaromatic compound, but anti-homoaromatic compound is more stable than anti-aromatic. So these are the thing. Now here, quickly look at what are the base structure of anti-homoaromatic. You have the cyclopropenyl carbanion. Okay, this is anion, carbanion. This is one. You have cyclobutadiene, and you have cyclopentadienyl carbocation. Okay, so this is plus. Okay, this is plus and this is minus. So these are the three base structure which are anti-aromatic. So anti-homoaromatic means you have to add sp3 center around this base structure. Okay. Now let us look at what are the different variations of homoaromatic compound. So homoaromatic compound we find into three categories. You have the neutral molecule, you can have the cationic, and you can have the anionic. Okay, there are three types of this molecule we find. Um, just look at the neutral homoaromatic compound. You have um, this molecule, okay, cycloheptatriene. If you look at here, if you look at here, this is, you have sp3 center. Okay, now this molecule actually, uh, if you look at, in the last class I told it is having band structure. Okay, it is having band structure. So the structure is looking like this one. Now here, due to its band structure, the delocalization by overlooking this sp3 center, okay, is very less. Got it? This is the delocalization has been shown. The delocalization is happening, but it's very poor in condition. So this molecule, uh, we directly put into the non-aromatic category, non-aromatic, aromatic, though you have sp3 center here, but overlooking this sp3 center, it is having 4n plus 2 pi electrons. Okay, but apparently it looks like homoaromatic, but it is not homoaromatic. Why? Because the molecule is not having the flat structure in its base. Got it? So that's why the delocalization is not proper. Okay. So we put it into the category of non-aromatic. Now let us look at one interesting example of neutral homoaromatic compound. If you look at this molecule, you have here 2 pi, here 2 pi, right? And you have NH here. So this molecule, and this is on one sp3 center. So this is a sp3 center, sp3 center. This is also sp3, okay, but you have lone pair of electrons. Okay, so it can uh, participate in delocalization. So what we find is that this molecule can behave like this. Okay, so this molecule can have the delocalization is happening in this way, and you have a pi cloud movement. Okay, or 6 electrons they are participating the delocalization and by overlooking this sp3 center, okay, this sp3 center. So this is an example of the homoaromatic compound based on you have uh, this structure. Okay, so here this is one of the example you should note down. Okay, generally we don't find this example I mean everywhere. Got it. Another interesting example is Wolverine. Okay, so Wolverine is, if you look at, you have, this is a pi, this is a pi. Okay, if you look at this particular cycle, okay, you have 2 pi and 1 sigma bond. Okay, so what you can have, the Wolverine is another example of a homoaromatic compound. Here, if you look at individual structure wise, so this is happening. So you have, uh, let me write in a different color so it will be more visible. Okay, so what you can think is this is coming here, this is making the sigma bond and this is coming here. Okay, in this way you have this structure. So here 2 2 2, so 4 pi electrons and 2 sigma electrons, they are participating, right? And you have the cyclic I mean the rotation of your pi cloud is happening here. Okay, and it is maintaining, just overlooking this sp3 center, this is overlooking this sp3 center. Okay, this sp3 center is being overlooked and the aromaticity is I mean the delocalization is maintaining by 4n plus 2 pi electrons. So this is the example of homoaromatic compound. You have another, I mean you have different structures. So the different way of, so here in this case, if you look at, this is the movement. Okay, this way you are getting this one, and this is another way, the other three. Okay, so the bigger one, you can think this way, this is happening, this is making the bond, and this is, so you have this way the movement is happening and the homoaromatic character is gaining. Okay, let us look at another difficult example, is semi-Wolverine. So the previous one was Wolverine, this is semi-Wolverine. If you look at the structure, you can do the same way. So you have, if you look at this way. Okay, so what you are having, this can uh, have this structure also after delocalization. So this is the overall canonical structure. Okay, and if you look at the exact example of this molecule, people have synthesized in the laboratory, the homoaromatic dianhydride. Okay, so you just have the anhydride here, and this is quite stable. Similarly, people have synthesize this as another molecule. So here you have phenyl substitution, here cyanide, you have phenyl here, you have cyanide here. So these are the two molecules people have synthesized in the laboratory, have been shown to have the homoaromatic character. Okay, the resonance energy of homoaromatic character are like at least 5 to 10% of the general I mean general aromatic character. Okay, and when we find that the energy is very low, then we don't put into the homoaromatic uh, I mean the category. Okay, so it is particularly based on any arbitrary structure cannot be just adopt. As I told at the beginning, some specific examples have been identified, calculated its energy, resonance energy, and kept in the category of homoaromatic or anti-homoaromatic. Okay, so these are the examples you should know, and you should apply in different reactions. Okay, so reactions I will come into a bit, I'll show you a few of the examples. You will see how we can apply this concept. Okay, so neutral homoaromatic compound based on the benzene ring. So if you look at the benzene, what you have, you can put a sp3 here, you can put sp3 here, you can put sp3 here, right? And This way, what you can do, you can have, this is one example. Okay, here if you look at, this is a pi, this is a pi, this is a pi. Now you have this 1, 2, 3, 4, 5, 6. So your base can be like this, and 3sp3 center like SCH2, you have CH2 here, you have CH2. So they can be breached from, and you can have like of a base having benzene structure. Okay, so the benzene structure with three, the pyramid kind of uplift existing in this way. So kind of a valley where you have these three, the points, upwards direction. So this is one example having multiple sp3 center. Okay, so here, if you look at the delocalization, it is kind of this way. Okay, so the base is benzene, and you have these three, uh, the three sp3 centers. Another is, this is one more example where you can have the base is benzene, and you can have, the two sp3 there, this is one sp3, this is one sp3 on the same the sp2 connections. Okay, this is the sp2, this is the sp2. The previously you were having only one sp3 between the two sp2. Okay, now here two sp3 between the two sp2. So this is another critical example. So here also you can have the delocalization happening, and this is kept as into the category of neutral homoaromatic compound. Okay, let me tell you another example where you have the two sp2, they are connected, two sp3, they are connected to each other. Okay, directly. So this is sp3, this is sp3. Okay, so two sp3, they are connected. Now this is also called as a homoaromatic compound. Okay, the structure wise, this is the frame, and you have, this is the canonical structure. You have the resonance is happening at the base, which is of benzene structure. Okay, now third one is based on the cyclopentene system. Now cyclopentene you can write this way. This is sp3. Okay, so this is sp2, sp2. So this 1, 2, 3, 4, they'll be on the plane, but the fifth one, okay, this will be out of the plane. So that is the representation of this one. Now this molecule, they can be connected to each other to have one more example where we find the base is benzene. Okay, if we look at here, the three cyclopentene, they are connected. So this is one, this is one, this is one, and you have another one. Okay, so they are, having a common sp3 center. Okay, this is also sp3, this is also sp3. So here if you look at three sp3 center, but your delocalization is happening through this way. Okay, so 6 pi electrons, and you have this structure. So these are the critical structures I'm showing you, so that you are, you become familiar with the structure and know as they are.
Hello, sir. Hello.
Yes, yes. Tell.
In the example, where we have one sp3 and sp2, no?
Yes.
In that, how 4 n plus 2 rule is obeyed, sir? There is only one pi bond.
No. This is not. This is not homoaromatic. Okay, not homoaromatic. This is not homoaromatic. What I am telling is, when you are building up one compound, this is homoaromatic. Okay, homo. When you are building up the compound based on this structure, Okay, based on this structure, then you are having homoaromatic character. This is not homoaromatic. This is just a unit which is they are connected to each other to have this one. Got it? My point. There is no 4n plus 2 pi
Yes, sir.
electrons are maintaining, and this is not at all I am talking as the homoaromatic. Get it?
Sir, one sp3 carbon must be present. No?
What you are telling, I am not getting.
Sir, one sp3 bond system must be there. Hybridization.
This is the definition is the delocalization should happen one or more than one sp3 by overlooking it. Understood? So your delocation will be
Yes, sir.
based on aromatic number of electrons 4n plus 2, and that can happen just overlooking by sp3 center or centers. It may be one center, it may be two centers, it may be three centers. Okay, got it?
Yes, sir. Yes, sir.
Yeah. So here the delocalization is not happening because there is no option. You have only one pi electrons, and that there is no chance of moving it. No position is there to no another. There is no helping center to move to take up these electrons. Okay, so we don't put it. There is no deloc. It is a static pi cloud. Got it? Okay, so let us move forward. Uh, Now, this is another compound where you have boron as the element. Okay. Now, this compound, if you look at uh, when you are having the electron withdrawing group or electron donating group, okay, electron donating group here are an electron with this is electron donating group. If you have this one electron withdrawing group, if you put this R as electron withdrawing group. Okay, so what we see is that this particular system, it behaves, it behaves as a neutral homoaromatic compound. When you have the electron withdrawing group, remember, electron withdrawing group is there, then it will behave as a neutral homoaromatic compound, but internally this is uh, deuterionic compound. So neutral in that sense, deuterionic. You have the positive charge, negative charge is there. What happens is that you know already when the boron is having three bonds, it is already electron lacking. It behaves as Lewis acid, right? You have six electrons there, so it is not fulfilling the octet, so it needs two more electrons, okay, to fulfill it octet. So that's why it has a tendency to accept electrons. Okay, so boron with three bonds, it behaves as Lewis acid. Now this is already lacking the electrons, right? When you are having more electron withdrawing group, your electron thrust of this center is increasing drastically, and what happens is that due to that property, this hydrogen gets migrated, okay, this center, or it can migrate to this center, and that is being represented here. When it is hydrogen is migrating with the bond pair of electrons, then you have a positive charge generation of this center. Okay, and that is happening. You have a positive charge here. Let me take the red color so that more prominently you can see. So when the hydride is migrating to the boron, boron is having hydride. Now it is having more electrons. So that's why boron will be negatively charged center. So this is a positive charge center. Now boron will be negative. Here, if you look at this hydrogen has been placed in a dot dot way connected to the two boron center. It means it can be connected with this boron. It can be connected with this boron also. Yeah. Now in a specific way we can write this one. The hydride has been migrated from this center to this center, then you have a positive charge here, this is a positive charge, and here it will be negative charge. Okay, now this particular environment will behave in a different way. So what you can have here, this positive charge, so this bond can migrate here, okay, as shown here. migrate here. So your boron is now becoming neutral. You have 3 bond. Okay, carbon is becoming neutral. Okay, in the same way you can have in the same way you can have another orientation. So this can come here. Okay, your boron is now negative. Boron is now negative. These are negative. Okay, boron is now negative. Since this is breaking, so you have a boron positive. Okay, so again it is becoming neutral. So this way you have the movement of electrons around, and you have the uh, anti-homoaromatic homoaromatic character is gaining. Why? Your all the movement is happening around these 3 centers. So the center 1, so let me write here, this is the center 1, center 2, and center 3. Okay, around these 3 center it is moving. It is overlooking this center sp3. Okay, so this is one of the toughest example, but I'm just showing you so that you just be familiar with it. Now, what are the electrons number here moving? It is the 2 electrons. Okay, 2 electrons, 2 electrons moving. Okay, you look at, this is a neutral, you have this pi is having 2 electrons, so this is moving. Okay, here this sigma is moving, this sigma, here this sigma is moving, this sigma moving means this is a 2 electron system. Okay, ultimately that electron is coming from this hydride, or this hydride. Okay, you have 2 electrons, that electrons is being connected and ultimately change the whole system. So this is the example of homoaromatic compound when this R is electron withdrawing group, not the electron donating group. If you put the electron donating group, there is no such behavior. Okay, because the electron cannot move now. When you have the electron withdrawing group, it is having more thrust, so that's why this hydride is being transferred. Okay, this hydride is being transferred. So this is one example of neutral homoaromatic compound. So ultimately the overall delocalization has been shown here. If you look at, overall delocalization has been shown here. In the same directional opposite, in this is I have shown here the bottom one. The same way you can have the upper one, and the similar pattern you will see. So all this you'll be looking at. Okay, so this is the examples. I mean, very important for the competitive exams. Okay. Now let us move to other type of compounds. Okay, so cationic homoaromatic compound. Now, when we are talking about cationic homoaromatic compound, what are the base aromatic having cation structure that we need to know? Okay, the number one is cyclopropene. So cyclopropenyl cation. Okay, this is a cation, it's traveling. So cyclopropenyl cation. This is aromatic, right? This is aromatic. In the last classes you have learned that one. This is aromatic. Okay, and when you are talking about homoaromatic, you need to add the sp3 center. Now this is, if you look at one sp3 center being added. Okay, so 2 pi, one positive charge, it can move, and it can be having our stability. Okay, and we call this particular structure as a homoaromatic. Similarly, if you talk about the 5-membered ring, okay, having a positive charge at this center, look at 5-membered ring having positive charge at the center. So what it is doing, it is overlooking this sp3 and overlooking this sp3, maintaining the delocalization. So you have this structure, and this 3-membered with a pi bond having a positive charge circulating. So you have, this is again homoaromatic. Okay, is homoaromatic. The third one, you can have 6-membered ring too, but there should be 3-membered and 6-membered fused. Okay, in that sense. So if you look at this can move here, it will be neutralized, you have positive charge here, so this is happening. Again it can move here, so it will be connecting these centers, so you have a positive charge here, so this is a positive charge. Okay, so this way you have a circulation of two electrons, in this case the sigma bond electrons circulating, so you have the internal position, the positive charge is circulating among these centers, right? These three centers. So you have three membered, two electron having a positive charge. So that is the situation. So this is again we call it homoaromatic. Okay, so homoaromatic means actual structure is this one, and this one. They are all homoaromatic compounds. Okay, so this is I mean, this is very important in terms of different questions, so that you will come to know. Now, another structure is,
Hello, sir.
yes, tell.
Hello,
Yes.
sir. That in the first one,
Hmm.
the Cationic Homoaromatic, that example, in that example, that how foreign rule is being followed.
See, you have 4n plus 2, right? 4n plus 2 is here 2, n is 0. Got it? You have two electrons is moving. You have two electrons. This is two electrons, right? 1 pi means 1 pi, two electrons. Got it? Similarly, here also 1 pi is moving. Here also is not pi, it is sigma is moving. Got it? Sigma. So all are maintaining. Okay. So in all these cases, you have 4n plus 2 and you have two electrons actually moving uh, by overlooking sp3 center or centers. Okay, now in this case another compound which is, I mean, the cationic structure, which we came to know that that is also aromatic, and that is the 7-membered ring having 3 pi electron, I mean 3 pi bonds with a cation. Okay, so we call it tropylium cation or cycloheptatrienyl cation. Okay, so this one is also aromatic. This is aromatic, you know, aromatic. Okay, so these are aromatic. Now your homoaromatic can be based on these also. Okay, let us look at how you can have. So if you have a 8-membered ring have a positive charge here, so 3 pi electrons, so it is overlooking this particular center. Okay, and is maintaining the aromaticity. Okay, so it's moving here, you have a positive charge here, and then you have a movement. Only this sp3 center will be upward direction and the others will be in the base. Another is, if you have this structure, you look at here, this is a cation, you have sp3 here, you have sp3 here, you have a sigma bond here, this is a sigma. Okay, sigma bond, this is a sigma bond. So this bond can move and these two pi bond can move. Okay, so if you look at this sigma is broken, so this is coming here, you have a positive charge here. Now this is moving this direction and it is overlooking these structures. Okay, so the aromaticity is maintained by overlooking these two sp3 centers. Okay, here in this case 2 sigma, sorry, 1 sigma 2 pi, so 2 pi bonds, altogether 6 electrons, so 6 electrons are moving here. It behaves, you know, 3 pi bonds you have. So ultimately your base is of 7-membered with 6 electrons and a cation. Okay, which is similar to this structure, similar to this structure. So we call it, this is also homoaromatic. Homoaromatic. Okay, so homoaromatic. Homoaromatic. Got it? So just look at the structures and how you can rotate the I mean, how you can delocalize the pi clouds or the electron clouds, that you need to know. And what is the base structure? It is aromatic or non-aromatic, or aromatic or anti-aromatic. Based on that, whether it will be homoaromatic or anti-homoaromatic. Okay. Now let us look at couple of examples in terms of questions. Okay, suppose you are given with this question, two structure, structure 1, structure 2. So where the reaction with acetic acid can take place. Okay, so you have OTS. You remember OTS is a good leaving group, okay, leaving group. OTS is a very good leaving group. When you have a positive charge, I mean, when you are providing H plus, this can easily take the H plus and becomes OTS H, sorry, it will become TSOH, tosylic acid. So this one can come out and it will generate a positive charge in the system. So when the OTS is coming out, it will have a generate a positive charge. So it will generate a positive charge here, it will generate a positive charge here. Got it? And then acetic acid can also act as nucleophile, so acetate group can be incorporated. Ultimately, the reaction, I mean, the product you are expecting is this one, OAC. Okay, here in this case, OAC. Now the question is, which one will be proceeding, this or this? Okay, so which one will be proceeding? Can quickly tell any one of you?
Sir, first one, sir.
First one will be proceeding because first one is generating the homoaromatic intermediate, right?
Yes, sir. Yes,
So
sir.
homoaromatic, aromatic intermediate. Second one, which intermediate it is generating?
Anti.
Anti-aromatic.
Yes, sir.
Okay. So those who are not following, who cannot understand easily, just think, okay, and it will be clear. You need to know what is the reaction. Got it? So ultimate point is whether it is homoaromatic or anti-aromatic or aromatic, all of the that will drive the actual the reaction. Based on that, the reaction will proceed. Now another example here, if I gave. So reaction with acetic acid, this and this. So compound 1, compound 2. Okay, you have OTS here, this is OTS, here OTS here. Okay, now which one will react with acetic acid, 1 or 2?
So compound.
Which compound, compound 1 or 2, which one will react with acetic acid?
Sir, 2, I think.
Sir, two.
2.
2 or 1?
Sir, one.
First of all, what you came to know from the
One,
first
sir.
example, you have to always think what is the intermediate it will form. So in this case, intermediate it will form is expected intermediate formation. This is cation here at the center. In this case, intermediate formation is the cation will be producing at this center, right? Yes or no?
Yes, sir.
Now tell me which cation can easily form? This cation, 1 prime or 2 prime, which cation can easily form?
Sir, 2 prime.
One prime, sir.
1 prime will form. 1 prime is
Yes, sir.
homoaromatic. You see, this is the sp3, it is overlooking sp3. This is sp3, it is overlooking sp3. So it is 3 centered, 1 cation and 1 pi bond. Okay, so this is homoaromatic. This one you have positive charge here, and that position is the bridgehead position. Bridgehead. So not possible. Not possible to form. Got it? So this is the center. You have, if you are generating cation here, this center, this center, this center have to be on the plane, right? So when you are generating a cation at this center, what is happening? This have to be on the same plane. But here it is this is kind of bridge, so it will be like this way. Got it? To become a plane, it has to come like this. Okay, so that's why the planarity is not easily accessible. So bridgehead position not possible to form. Okay, so this is not going to react. Acetic acid reaction not going to happen here. Here it will happen. Got it? Now look at this one. Okay, acetic acid and heat you are putting with this particular example. So you remember let me clear this one so that you can see. Okay. Okay, so what you have here, this one, if it is coming out, what is generating here? It is a cation generating here, right? So it will be generating a cation at this center. Okay, now this one can move in this direction. So this can go here. So you have a structure addition here, you have a cation here. Similarly, it can go in this direction, it can generate a cation here. So this way you have a 3 center, okay, one sigma bond, sigma bond is moving, and you have positive charges rotating. So you have this structure which is aromatic. Okay, got it? So you have acetic acid can come this direction, acetic acid can so when it is planar, okay, actually you have these 3 product you can expect. Okay, these 3 products you can expect. If you give numbering, since time is not there too much, so I'm just not moving. You can just try that one when you are having this structure, okay, and then you react with acetic acid, what happens, you just know. Okay, so these are the 3 structures you can access. Got it? You can access in one way. I just write maybe here. Okay, you can have this structure, one cation. Okay, you can have this structure with this connection. Okay, and this is already there. You can have this connection with this cation. So these are the 3 cations will form, and based on the cation, your OAC will be connected there. Okay, and R is always maintained. So if you just give numbering, then you will understand where the R group will be there and where the OAC will be. So ultimately, you will get these are the 3 different products. Okay, just yes. Anything? Okay, so just quickly, I'll tell few more questions. So suppose you are adding H plus, okay, if you are reacting with the sulfuric acid of these two particular molecules, what is going to happen? Okay, so this is giving the H plus. So H plus will be added. Okay, H plus will be added. So where the H plus will be added? Here what it will form, here what it will form, where the H plus will be added. Okay, just look at, this is Me, this is F, and you came to know from here. Okay, I'll just give one information here. Somebody's just switch up your microphone. If you add H plus, what is going to happen is H plus will be taken. So you have this structure will be, if H plus is connected here, so this will be the structure, right? Now if you have methyl and fluorine, these two groups, where the, I mean, how the structure will form, which structure will be predominating, okay, based on this particular chemistry. So that you need to find out. This is your home task I am giving. Okay, let me just, another example, just wait. If I remove this one, it will be visible. Okay. Now suppose you are having this molecule and you are reacting with superacid. What is its job? Its job is to do protonation. Okay. So what product it will form? You have this one. If you add superacid, what product it will form? So in previous discussion, last 1-2 slide before, if you follow, you will be able to give the answer. So these are the 3 questions you try to solve. Okay. Here, one thing I will tell you in terms of NMR. In the last class I told, you have to know when you are adding a proton that is becoming sp3 center, so it will be forming this way. Okay, and this is a positive charge, so this is, you know, you came to know this is homoaromatic already, homoaromatic. Okay, now you have 2 hydrogen here, Ha and Hb indicated. Now Ha will be directed to this ring current, Hb will be is away from the ring current. Okay, so what we see is that for Ha, due to diatropic nature, so your Ha value will be lower and Hb value will be higher. Okay, because this Ha is falling in the ring current. So if you apply the magnetic moment, magnetic field in this direction, ring current will be, the electron cloud will be moving in this direction. Okay, and you have the opposite way of magnetic field will be produced by this electric current, which will be shielding the Ha, so the Ha value will be less. Okay, so minus 1.5. So this is very important in terms of competitive exam too. Okay, and that's why if you see when you are having the molybdenum and iron, okay, Fe carbonyl and molybdenum carbonyl connection, what you see is that in case of molybdenum carbonyl, if you count the 18 electrons, rule, you will find that what will be the actual structure. Got it? In molybdenum carbonyl you have 3, so you have 6 electrons. How many electrons will be contributed due to molybdenum? Okay, got it? If you count that, you have here the total available electrons are 6 in this ring, so 3 pi electrons, so 6 electrons. Okay, 12, and molybdenum you have the outer shell electron is 6. Got it? So you have total 18 electrons. That's why the whole 6 electron will be taking part into this complex formation, and that's why this will behave as homoaromatic in case of molybdenum's compound. Okay, homoaromatic. But in case of iron, it will be not like that. In case of iron, it will take 4 electrons. Okay, this structure will be predominating. So 4 electrons and here 6, so 10 electrons, and iron itself is having 8. Okay, so 8 plus 10 is 18. Got it? So it will be having this structure, and if it is having this structure, this is not homoaromatic. So these two value will be similar. Okay, quite closer. 1.35, 1.53. They are very closer to each other. So this is the overall discussions of homoaromaticity. In the next class, we'll look at other examples based on anti-homoaromatic, and we'll move to the new topic of carbocation discussion. Okay, so maybe it will be difficult to understand this one. You just try to follow what I told, listen the video later on, and try to understand and communicate with me. If you have any doubt, you can clear it. Okay, it's a very short class. To convince everything in a very short period is very difficult. So that's why I always ask the students, if you have any doubts, you just try to clarify later on. Okay, try to understand, listen the video, and clarify later on. So I'm stopping here. You have next class. So thanks for attending today's class. Thank you.
Thank you, sir.